So far in this unit, we've been looking at the individual factors that affect AC power: voltage, current, resistance, inductive reactance, capacitive reactance. Now we're going to put everything together and see how all these factors combine to determine the rate at which work is done in an AC circuit. Power, according to a definition that you may be familiar with, is the rate at which work is done. In a DC circuit, power is equal to voltage times current. P equals E times I. As you know, the only factor that limits current in a DC circuit is resistance. So the only factors that affect DC power are voltage, current, and resistance. We can't just talk about power in general when we're dealing with AC circuits. In an AC circuit, there are three different kinds of power: true power, reactive power, and apparent power. We'll discuss each of these in turn, and then we'll see how they're related by something called a power factor. Okay, then let's start with true power. True power in an AC circuit is the same thing as power in a DC circuit. It's the amount of power that is actually used for doing work. True power is the type of power that's used in a purely resistive circuit. A DC circuit is a purely resistive circuit, because resistance is the only factor that limits current flow. With AC circuits, there's no such thing as a purely resistive circuit, because all AC circuits have some inductance and capacitance. However, there are AC circuits in which the inductance and capacitance are so small in relation to resistance that only resistance has any meaningful effect on current flow. In segment 1 of this unit, we looked at AC circuits in which only resistance affected current flow. The voltage and current sine waves for such circuits look like this. Voltage and current stay together. They always increase and decrease in the same direction at the same instant. In other words, voltage and current are in phase. We can use these voltage and current sine waves to determine the amount of true power at any instant in a resistive circuit. All we do is multiply the voltage and current together at the same point in time. It's that simple power equation, P equals E times I. But when we're talking AC, we have to be sure to get values for E and I at the same instant. During the first half of an AC cycle, both voltage and current are positive, so their product, power, is also positive. During the second half of the cycle, both voltage and current are negative. Here again, their product, power, is positive. Whenever you multiply two numbers with the same sign, either two positive numbers or two negative numbers, you get a positive product. Now, the term positive power is just a convention. When we talk about positive power, we mean power that's going from a power supply to a circuit. When we talk about negative power, we mean power that's returning to a power supply from a load. How does power return to the power supply? Well, that question can be answered as we look at the second type of AC power, reactive power. Reactive power is the kind of power that you would find in a purely inductive circuit or a purely capacitive circuit. It doesn't do any useful work. Let's look first at an inductive circuit and then a capacitive circuit, and you'll see what I mean. For an inductive circuit, like the ones we saw in segment 2, we get voltage and current sine waves that look like this. Voltage and current are out of phase. Current lags behind voltage. In the first portion of this sine wave, voltage is positive, but current is negative. If we multiply voltage and current together to get power, we get negative power, because the product of a positive number and a negative number is a negative number. During the second quarter of a cycle, voltage is still positive, but now current is also positive. Since we have two positive numbers to multiply together, power for this portion of the curve is positive. The same relationships can be seen during the second half of the cycle. When voltage becomes negative, current is still positive, so power is negative again. Finally, during the last quarter of a cycle, both voltage and current are negative, so power is positive. We said that positive power is power that is going from a power supply into a load. In an inductive circuit, positive power goes from the power supply to the inductance. The inductance absorbs power from the power supply as its magnetic field builds up. We also said that negative power is power that's returning to a power supply from a load. In an inductive circuit, the negative power periods are those during which the power absorbed by the inductance returns to the power source as the magnetic field collapses. Now, as you might guess from looking at the sine waves and seeing the regular rise and fall of both voltage and current, the amount of power that's returned from the inductance to the power source is equal to the amount of power that's supplied by the power source to the inductance. In an inductive circuit, then, power just goes back and forth between the power source and the inductance. No power is used to do work, so there's no power that we can identify as true power. The power in a purely inductive circuit is only reactive power. The same thing is evident in a purely capacitive circuit. As we saw in segment 3, in a capacitive circuit, current leads voltage. We can go through an AC cycle for a capacitive circuit the same way we did for an inductive circuit and see what happens to power when this out-of-phase condition exists. During the first quarter of a cycle, both current and voltage are positive, so power is positive. Then in the second quarter, current is negative and voltage is positive, so power is negative. At the start of the second half of the cycle, both current and voltage are negative, making power positive again. And finally, during the last quarter of the cycle, current is positive, voltage is negative, and power is negative. In a capacitive circuit, when power is positive, the capacitor is charging and storing up power. When power is negative, the capacitor is discharging and returning power to the power source. The effect is the same that we saw for the inductive circuit. The amount of power that's returned from the capacitor to the power source is equal to the amount of power that's supplied by the power source to the capacitor. Again, the power doesn't do any work, so it's reactive power rather than true power. The last kind of AC power is apparent power. Apparent power is what we get when we multiply voltage times current in an AC circuit. Look at this AC circuit for a minute. It contains an AC power source, a resistor, an inductor, and a capacitor. If we multiply voltage and current together for this circuit, we won't get true power, because true power is calculated this way only for purely resistive circuits. We also won't get reactive power, because there is a resistor in the circuit. What we do get is a value that we call apparent power. Apparent power, then, is the power used to do work plus the power that's stored during part of the cycle by inductance or capacitance, and then returned to the power source. In a circuit like the one we just saw, we have to consider the effects of resistance, inductance, and capacitance. Taken together, the combined effects of all three factors on current flow and therefore on power are called impedance. As we've seen, inductance and capacitance tend to counteract each other. Therefore, we can't just add inductive reactance and capacitive reactance to resistance to get impedance. Impedance can be calculated, but the calculation isn't one that you'll have to do very often. Instead of calculating impedance and then going on to calculate true power with impedance taken into account, you will most likely be using the power factor for circuits that you're working on. The power factor is the ratio of true power to apparent power in an AC circuit, usually expressed as a decimal value. Anytime that you know the apparent power in a circuit and the power factor for that circuit, you can multiply the apparent power times the power factor to find the true power. Another way to say this is that voltage times current times the power factor equals true power. You'll find that power factors come in very handy when you're using current and voltage meters. Your text has some problems for you to work with: power factors, apparent power, and true power. Read through the material in section 4 of your text and answer the questions. If you have any questions, ask your instructor for help.